Okay, hi there. My name is Amrit. Sorry, my voice is a little bit hoarse, so I'll try my best. So my name is Amit Kumar. Me and my friend Yauchi were sitting there. We work on a project called Offline, and today we are going to present this idea of ZK fault proofs. As you can imagine, it's a mix of the fusion of the variety proof idea that you see in ZK rollups and the fault proofs / fraud proofs that you see in optimistic rollups. By the way, this is joint work with RISC-0 team, and so thank you very much to them for making a lot of tools available, but also working with us on this. Before, a little bit of marketing, I suppose. So at Online, we essentially started with as a rollup service provider, so we make it easier for people to deploy rollups because we believe that there will be hundreds of more rollups designed for different application use cases. And so our goal is to make it possible that even a marketing team member or a business team member should be able to go and deploy a rollup by just a few clicks and buttons. We support many different tech stacks, including some popular ones out there in the market, but also other services like data availability, interoperability, and other services that are out there for rollups to use. What we do beyond RAS is also interesting because we believe that once we have these rollups, they will need certain other services. For example, they will need interop, they will need, for example, a fast finality layer, and much of other things. So we also try to make it easier for people to deploy or use some of those services that are not out there in the market today. And so one thing that we do is basically we build what we call a MAC, which is basically a fast finality layer, which taps into a layers restaking mechanism to make it easier for people to have a better finality than what you get from there. But today's talk is going to be about this work. Originally, it was titled The Odd Couple, ZK and Optimistic Rollups. On a scalability date, if you want to read a full version of the presentation, you can head over to RISC-0's blog post and you can read more about this. Now, so bit of background context. We all know that by now that monolithic chains that do execution, consensus, and DA, are not very scalable. And so, in the last year or so, we have seen quite a bit of push on motorizing the different components and the stack that forms the blockchain. So, one thing that, of course, DA is quite high, but one thing that has really seen quite a bit of traction and quite a bit of developer activity is the execution component in the form of different rollups that you see in the market, right? And so, and because the execution moved out of EVM or Ethereum, you can imagine different other things that you can do with the rollups. So, for example, you can imagine rollups that are ZK based, so variety proof models, or rollups that are optimistic rollups, so based on fault proofs. You could imagine different runtimes because you're no longer limited by the underlying EVM. You could imagine building wasm-based rollups and so on. You could start with general purpose chains. You could start with something like Arbitrum, Optimism, ZK single score, but you could also boil down to a more degenerate scenario where you could say, hey, I want to go and build my own app-specific chain, or I want to build a chain or a rollup that's basically ephemeral, so it doesn't stay for long, and I only want to use this rollup for a short while, and after that I will shut down the system. And you could do that simply because you have moved the execution out of the base chain. And so today's talk is going to be focused on the first component, which is you have these two flavors out there, which is the ZK rollups that leverage variety proofs, and then you have optimistic rollups that use fault proofs. And the idea is, can we get the best of both worlds in some way? And so very quickly, ZK rollups, as you may know, basically you have this sequencer, aggregator, prover, whatever you call it. In some cases they're all combined, in some cases they're separate. They basically execute transactions and they produce a proof of validity, and that proof goes back to the L1, and the L1 basically verifies that the proof is correct. On the optimistic side, it's slightly different, where basically everything's supposed to be correct, and so the rollup sequencer basically puts transaction data on the L1, and then if someone feels like the state committed by the rollup is not valid, then you can raise challenges, and then you go to the transaction where you basically prove that the sequencer has done something malicious and the state is not valid. And so there are different pros and cons for both models. So there are different trade-offs that both rollups make. For example, in case of ZK rollup, these are based on cryptographic proofs. You don't make any assumption, a direct assumption on the honesty in the network, while in optimistic rollups you assume that there's some party that is watching the network and that can go and challenge if the network commits a certain wrong state. ZK rollups generally are quite bleeding edge. In some cases, people have actually developed their own primitives to make these proofs quite efficient. While the optimistic rollup, they're much more classical. All you're doing is basically doing a bisection over the instruction set. So it's much easier to understand, much easier to implement compared to something However, on the ZK rollup side, computation can be quite heavy, so proof generation is quite intensive. And so in some cases, it can take quite a while to basically go and generate these proofs. And so you tend to basically wait for a while and generate your proofs for a batch of transactions, so doing per transaction. On the other hand, fault proof is basically communication heavy. So in the sense that when you do fault proving, you want these challenges of the sequences to be basically online for each transaction to be exchanged between each two parties. And therefore, that also results in withdrawal period. So ZK process is much shorter in minutes, while in the case of optimistic, that can last for 7 days. So you want to make sure that these parties who are engaging in the bicycle protocol, they actually are live and sending messages across. So the idea is, yes, both systems have certain pros and cons, but they can be somehow combine these two systems into one single system. That's the idea of this talk. So basically, we're going to present you a construction which combines ZK proofs and fault proofs in what we call ZK fault proofs. So the basic idea, high-level idea of ZK fault proofs is that, look, in pure ZK rollups, you basically generate proofs for every single transaction. Not really every single, but basically the idea is for a batch of transactions, you generate proof. But what if we don't do that for every single transaction? We do generate proof only when it's required. So it becomes much more on-demand model. So it becomes an on-demand model where the proof is generated only when there's a challenger who says that, look, I found something wrong. Can you generate a proof for the last batch of transaction that was committed? So just to clarify, it is not ZK-AVM. It's not a ZK variety proof model. It's a model where you're asking a sequencer or asking the prover to generate proof only when you think that the system has generated or the rollup has committed or invalid state. So there are two variants that you could use and implement this idea in. So one is where you make minimal changes to the existing rollup design. So imagine you are starting with an optimistic rollup where you have the sequencer, the challenger, they do this off-chain bisection protocol. And what you do is, in a normal optimistic rollup, the challenger basically challenger and sequencer comes with one single instruction that both parties disagree on. So the sequencer says that this instruction has been executed correctly, while the challenger says no, it has not been executed correctly. And so basically that single instruction then gets executed on the chain. Now instead, in this ZK fault proof variant, you say, hey, we have come up with this single instruction that we both disagree on. Instead of running this on chain, can we just generate a ZK proof for this single instruction? And then the sequencer or the prover behind that will produce a ZK proof for we generate a ZK proof for this single instruction, and that proof gets verified on chain. The second model would be slightly more involved, where you don't do bisection at all, so bisection is completely taken out. And so challenger basically comes and says, hey, this last state commitment that you made on the L1 seems to be invalid. Can you give me a proof for this last state commitment? Note that sequence is not generating proof for every single block. It is basically just operating in the optimistic model, so it's just sending transactions, committing the state. Only when the challenger puts a claim and says, hey, something looks wrong here, can you generate me the proof? At that point, the sequencer or the prover behind it will basically generate the proof of validity, and then will commit that on the L1 or on the L1, basically verify this. So this is basically replacing the entire message protocol by an on-demand ZK validity proof, and the demand basically comes from the challenger. So there are pros and cons to both variants, obviously. One is, in the variant one, if you are building or you already have an optimistic rollup that's already live and running, you kind of have to do very little changes to support something like the variant one. Because all you have to do is you can keep your bisection protocol intact. Your contract that basically emulates the VM, that will go away, and now you'll be running verifying a proof instead of running the instruction on chain. So it requires minimal changes, somewhat backward compatible in that sense. The good thing in this model is that now you're not limited by the runtime of Ethereum. So for example, you could say, hey, previously, say if you're looking at OPStat, for example, or Optimism, they have basically emulated an EVM system or in Solidity on Ethereum. You don't have to do any of that, because all you have to do now is basically verify a proof on chain. And this also gives you more flexibility in terms of expanding to other VMs as well. So you could, for example, build a WASM-based rollup and still have Ethereum basically verify the proof if you want. However, the performance benefit is quite limited, as you can imagine, because you're still doing the bisection protocol. And so it's not ideal because computation is still heavy. And so this is where variant 2 kind of shines and does better. The problem with variant 2 is that you have to basically overhaul the entire design. You have to change the entire architecture of how your system works. And so it's a little bit more intrusive to an optimistic rollup that's already live. You don't have to be live for the bisection protocol to finish. So you basically, all these parties are basically offline. And the challenger is the only one basically watching the network. And if something seems to be incorrect, then the challenger will basically ask the prover to post proof on that. Again, similar to variant 1, you can basically allow different kind of runtimes, so you're no longer limited by EVM anymore, and you can potentially reduce the withdrawal period if you want. We have done implementation thanks to RISC-0. So we started with an optimistic rollup implementation that was in Rust, which did fault proof over WASM. And it runs Sputnik VM in Rust, and it has basically compiles EVM to WASM instructions, and then you have a bisection over WASM. For ZK proof, even though RISC-0 now has most of the tech stack is now open source, we actually use the bonsai service, which is basically what's the right term? Basically a remote service, proving service, where basically you can send your transaction and what you want to prove, and then the bonsai basically returns you a proof for that. So that ZK proof is done over WASM. And behind the scenes, they use ZK VM, which is basically compiles everything Rust code to basically RISC-V, and then they prove over RISC-V. To conclude this talk, I want to highlight that this system, even if you go for this is still optimistic. It's not a ZK rollup. It's still optimistic in nature. One, because we still want a challenger, to be watching the network. So you still want at least one honest party to make sure that the sequencer is not misbehaving. In terms of proving time, it's still, as you know, ZK rollups are still quite expensive, depending on the time perspective. So it takes about 15-20 minutes for the proof to be generated. So it's still somewhat faster than a longer survey withdrawal period, but still substantial. I didn't discuss the constraint or the caveats around what happens when a challenger basically keeps bugging the sequencer, say, hey, I found this invalid state, can you generate me a proof, even though the state was actually valid. So you have to have some mechanism of slashing mechanism where a challenger is incentivized to only ask for proof when there is an invalid state coming. Because otherwise, it will be completely, it will basically turn into a ZK violation, which we don't want. Our current compilation pipeline is not very efficient. So we start with EVM, which is basically Rust. We compile down to WASM, and then behind the scenes, again, RISC-0 does this RISC-V conversion. An ideal model would be basically take your EVM and compile onto RISC-V running. This way you can be much more faster. And then the idea would be if you could integrate that with OP stack and Arbitrum rollups, so it becomes available to anyone who wants to spin up an app-specific rollup using any of the heuristics. Well, that's it. If you have any questions, if you want to challenge us, we are here. You can ask us questions. Thank you.
So, can you tell me a little about the limitation that made you the decision of converting it to WASM first and then RISC-V?
The reason simply was that we had an implementation that was in Rust, so we went with that. But as I said, it's not.
So you had the implementation for compiling it to WASM first, and then.
No, so we had an optimistic rollup. It's kind of like if you look at Optimism today.
I mean, like you have the EVM in Rust, and then you have a middle layer for like WASM first, right?
Yeah. So basically.
So why you are not directly compiling it to like RISC?
Yeah, this is exactly that we have to do, right?
Yeah. So I mean, like, why did you?
No, because RISC-V is not we are doing it. This comes from RISC-0. Yeah. So behind the scene, RISC-0 basically takes a Rust code and compiles down to RISC-V. That's what they do behind the scenes. So what I'm saying that if they are only doing on RISC-V, why not they basically take EVM and compile it to RISC-V, so this becomes a little bit more efficient. So we are not doing that, but this will be a better model to go for.
Thank you.
I have a question. Like, can I understand like variant one is more about reduce the fraud proof cost, and variant two is more about the shorten the challenge time?
I would say so, yes. So because you're still doing bisection, you can't really reduce the challenge period that much. You still have the liveness requirement for your node to need. So I agree with you. Yes.
Are there any more test data about the performance improvement? Is that?
So I would say this is the most obvious improvement that I can think of. The other thing is, of course, on the proving side, right? So the better the prover gets. And by the way, this 15-20 minutes, I can't recall the exact hardware unless you actually remember. So it's still a very performant hardware that Bonsai uses behind the scenes. So imagine, I don't know how many GPUs behind the scenes running. So if you do it on a normal commodity laptop, it's not going to be 15 minutes, right? So one obvious is that as the prover becomes much more efficient, as you can run much more efficient, generate proofs much more efficiently, you will have much more faster. But I would say that's of course the main bottleneck behind the scenes. I mean, yes, it's good to have that, but this is not the main bottleneck. This is the part that dominates the cost.
So another point for the bisection and the instruction verification, right? So if you use the variant one, if you do the bisection and basically identify the instruction which can be sort of wrong, right? The proof for that one is super fast. It's like within a few seconds. So there's a big balance because we provide sort of the rollups for different applications, right? Typically for games and a lot of social applications, we couldn't afford the prover cost. So every month roughly like $10,000 just for the prover sort of cost. So in that case, that's why we come up with this kind of design. So try to shorten the sort of this fraud proof or fault proof. Basically, we come out the ZK because once you have the ZK proof, right, you don't really do the very lengthy bisection protocol. It's basically a balance between the cost and also the sort of the security.
Any more questions like from
Is the verification cost the same for like the instruction-based dissection and the full transaction?
This one is for a full block.
Yeah.
Yeah. So for full block, typically less than 1 hour is like from 15 minutes to 40 or 50 minutes.
Okay.
Yeah, but for one instruction, if you finish the bisection for one instruction is very, very fast. It's within like I think 4 seconds or something like that.
Yeah. So the verifier is unchanged, right?
Yes, verification on chain.
Is there a gas cost difference between like the?
I don't think so because all you're doing is
Yes.
sending a proof,
Yeah.
right? So proof is just
It's the same verifier, right?
Yes. So the thing, another tricky part for RISA 5 die, RISA 0 die is basically the auto proof first in Stark, and then the Bonsai is mainly to convert Stark to Snark, and then you do the verification on chain, the technical the Snark verification. So as you can see, right, it's not a direct EVM WASM to RISA 5. There's another thing, Stark to Snark, and then you do verification on Ethereum. For OP stack, actually, the ongoing work, we already support the OP stack proof. It's like we are trying to do more optimizations on that.
Quick question for the fourth one. So you said apart from the slashing for preventing unnecessary proofs, to have the sequencer produce a proof, you can produce a proof for anything say to a value.
Yeah, it could. It's just like then you are basically becoming a
Right. So I guess like
you could.
is that also part of this? Like we need to figure out a way to make sure that the sequencer is also producing the right proofs on the verification side.
The sequencer can produce a proof because in the end, proof gets verified on chain.
Yeah. So like what inputs would you take from the other one to make sure that
Because if sequencer puts the proof, sequencer pays for the proof of verification on chain, right? And so there's already kind of a spam prevention built in for prover itself. Because one, it has to spend a lot of time to generate the proof. So it's not, they're not like why do all the work when it's not needed. I think the main problem is on the challenger side. Because the challenger basically can spam you and say, hey, give me this, give me this, give me this. and then
spamming side share, but if there's enough incentive, the sequencer can also be, provided enough incentive of the transactions to improve, you can still do one step.
Yeah, I mean, you could do. And actually, the other thing is, which I didn't mention, which is it depends on how. So let's say, for example, in optimism or other from you commit state after a certain period of time. If that's very, very long, let's say, I don't know, 1 day or two, let's say, for example, in some settings, because it's an app-specific context, you could say, hey, I'm going to post commitment every 5 days or whatever. In that case, when the challenger said, hey, your last 1 week transactions are all invalid, then it becomes much more complicated as well. So you have to also take into account the duration and the length of how far back you will go.
Okay. Any more questions?
One more question.
Okay.
Nobody else. So I think last month we had a ZK fault proof mechanism on testnet for OPS stack. I think it's by Oban Labs, right?
I think there
I was curious
proposal,
about
but
the
I'm not
side
sure
of here.
Speaking as an employee of OP Labs, the OM Labs and Risk Zero solutions are different from this, where you could think of this as you do some bisection or some argument on chain first over what needs to be proven, and then you come with a ZK proof to finish it. Whereas what they are doing is basically just a complete ZK rollup, replacing the proof entirely with a ZK proof. And then the beautiful thing there is that what Risk0 and O1 Labs can do is they can take the same definition of the state transition that the fault proofs proof and use that same definition and prove it in their virtual machine. So you don't have to roll a lot of custom code just to prove something in chain.
I'm from a one lab.
Yeah. We have all.
I present the ZK.
Thank you.
Well, thank you very much.
Yeah.
And again, we are around if you have any thoughts.
Yeah, we can discuss more after.